push the video. Tell me what EMF means.
Electromotive force. Electromotive force.
Good. Electromotive force. Who coined that term? This guy right here, Michael Faraday, talked about electromotive force, but lots of good guesses there. He said, because he was the first guy to really see conceptually that this electricity was going to be very, very useful. And you've probably, well, not probably, you've never gone a day without using the concepts that Michael Faraday put into practical. Right? You go camping? Do you have a battery along with you? Glamping. Yeah, definitely with glamping.
Those are irresponsible. I was just sleeps in the woods.
The EMF is the full force of the cell that's pushing. So this is electromotive
She's checking.
force. Have I ever told you about Rodrigo when I had him in here?
Wales scored.
Wales did?
Wales
I picked Wales. Is it 1-1 now?
He literally just scored.
Is it 1-1?
1-1.
Can we bring it up, please?
There's like 5 minutes left in the game.
Really?
Can we take a little cheeky break?
Oh my god, we should watch the last 5 minutes.
It's the 82nd minute.
Who has it on a computer? I don't have the feed.
I have it.
I have it, but it's like really shitty quality.
It's by the time we get it hooked up, it's gonna be over.
No, 5 minutes.
Wow.
We can do it.
There's one on
Let's
the
go
computer, one
fast.
on the TV. Yeah, well, the side.
Let me explain this really quickly, and then we can do it. I need you to all be silent. There's good motivation for me. Electromotive force is like the full voltage of the battery. Well, so then what is it that we measure around the terminals of the battery? If I put a voltmeter here,
Voltage drop.
and I measure that voltage, what am I actually measuring? We call this the terminal voltage. So this is V terminal, and you always see this V term, and that's what's being measured across the terminal. So what's the difference between EMF and V term?
Terminal is with the internal resistance drop.
Okay, so inside that cell, if we cut it open, the cell actually has some resistance itself, right? It's pushing the electrons through, but it also, there's some friction in there too, right? It's not very high, but there is some. So you can think of it as if inside the battery, there's a little resistor inside there. And then the cell, oops, I should draw this way, pushes the electrons through. This is the internal resistance. Okay. Now, if I were to put this in mathematically, I would say it like this. The EMF, the electromotive force of the battery, that's my full voltage, would be equal to the measured voltage. Just pause that conversation if you would. Just pause it.
So V terminal.
Full voltage is V terminal plus the voltage that's being dropped in the cell. Now, this is a weird thing to say because the cell is a voltage gain, right? But it also takes a little bit of energy for it to push those electrons through itself. So there's a little bit of friction in the battery. And so you would say that's, if this internal resistance we say is R, little r, then it would be the current in the circuit times that internal resistance, yeah? That's right, V is IR. So we would say this.
What does the E mean?
This is EMF. So this is a full voltage of the battery is equal to the terminal voltage that we can measure plus the current of the circuit times the internal resistance. This is the voltage drop that happens inside the battery.
That's what it's using to push it through.
Exactly. So this is what you lose inside the battery, and that's why we only measure V term. Does that make sense? So full voltage would be made up of the measured voltage plus the voltage that's being dropped in the battery.
I'll play it.
Now, if we rearrange this,
Oh, that's a foul.
we could say that is equal to, wait a minute, how do I do this? Negative value. We would say that the terminal voltage is equal to negative Ri plus V. You guys agree with this? Is this proper? Is that okay? It works? You just take the IR and you minus it over, and then you just move the Ri. This is Y equals mx plus b, right?
Really?
So if we can measure current and terminal voltage and get a bunch of different values, which we can, right? We would have a negative slope there, right?
So is R the slope?
Yes. So if you have, if you get a few values, and if you say this is V, and this is current, right? Then you're going to get values like this. At a small current, you're going to have a bigger voltage, right? And it's going to look something like this. And you're going to be able to draw a line through there. What is the value of the voltage right here?
It's E.
Good. This is their EMF. Are you ever going to be able to measure that?
Oh no.
Not perfectly, because you're never going to have a circuit with zero resistance, right? So you're never going to have zero.
Can't you just add the V term to the resistance and the current?
Say that again?
Can't you just add the V term to the resistance times the current to see what the actual E is? Oh,
Yes.
the resistance can't be zero.
Yeah, but you can't directly measure this, right? But we can get the slope of this, right? So the slope of this graph is equal to, and it's going to be a negative slope because it's negative R, right? So if you take the negative value of the slope, you get the internal resistance.
Actually measured. It can't be.
You can do this lab without actually knowing the resistances. You just need to turn your resistor down. Oh, and I was going to show you one other thing too.
I think it's just denoting the lower case.
You guys know what variable resistor, yeah?
No.
Resistor that can change resistance.
Yes.
Okay, good lucky guess.
It's a resistor that's variable. It looks like this. Can they see this on the video?
No.
Yes, like halfway.
Like if I just draw here?
Yes.
Oh, half until below the pull down. Oh my god. Terrible.
You're good, you're good.
This is a variable resistor. So you have a normal resistor, and then this is a slider. So this can move out, which would mean
More resistance.
Less resistance.
less resistance. Why less?
Going through less of the resistor.
Right, because the electrons will just go around if it's out here.
Oh, okay.
What if I move it all the way back? Then you get the full resistance because all the electrons have to go through the resistor, right?
Wait, what?
So this is a
There's another
variable
path where if you go the further down you go, the less resistance has to go through.
resistor. Now, this is, you can see the sliders like this, like you know those dimmer light switches that go up and down? That is this vertically, right? So as you move the slider up, you have less resistance. It would be like this. And then you have to make it so at the top you had zero resistance. So I guess It would have to be from here, right?
So
So this is your switch. If you move it up to the top, you have no resistance in the circuit and you get all your light. And as you move it down, you get more and more resistance until it's a lot of resistance and then you have very little light. You would also have a switch in here too, so you could switch off completely.
So for the first one, the more to the right is no resistance and more to the left is max resistance.
You got it.
So like,
Got
is
it.
it like another?
There's also like a volume knob on a stereo. You take that and you wrap it in a circle. And then your slider is a little doodad that hooks onto your resistor like this. This is probably blurry, right? Like this. And there's two on this one. Pass that one. Did we do potential divider circuits or not? Yeah, we gotta do potential divider circuits. I'm gonna move this over here. Just giving you a bunch of the last details of this current electricity stuff. If you had a variable resistor and one other resistor, and I told you that you have a power source, a cell, and you also have a component, and you want that component, Allie, to have variable voltage. So you want to be able to turn the dial on your variable resistor. You want to be able to slide it, and you want to be able to change the voltage in that. Not the current, but the voltage. So we want to vary voltage in here. Draw me a circuit that would do that. Try it. You have a variable resistor, and you have this. And you can put this anywhere you want in the circuit. Yeah. I just made it C for component.
Does it matter?
It's just something you want to be able to vary the voltage in. We don't know what it is.
So if resistance changes, then E equals IR. So you just put the variable resistor anywhere.
Okay, let's talk about that. If I just do,
Oh no, it has to be before any resistance.
Yeah, it's 3 before it, but like that's what I mean. Like it can be anywhere.
so you would be able to vary some voltage with that, right? Would we be able to get 0 voltage here?
No. Well, why not?
You tell me.
Because there still needs
This has some resistance to it, right? So there's going to be some resistance there. Even if you slide this all the way over, there's no resistance here. So the current would come through, that would be full voltage. If I pull it all the way back, you're not going to get 0 voltage there. It's going to be a lower proportion of the voltage, but you're still going to have some voltage there, right?
Doesn't matter.
But yeah, we want to be able to vary it from 0 to full. It just matters. What if I put my component into my slider? What if I do that?
Then you can get 0 voltage.
Right. Tell me how, Barrett.
Because wouldn't it, like, both the resistors, like the resistor and the component and the resistor for the other one, like, join together? So then you can, like,
This is a parallel branch now, right? What do you know about the voltage in parallel branches?
1 over.
Not the resistance, the voltage.
Oh, you supposed
The voltage in parallel branches has to be the same, right? So if this is full out, whatever the complete voltage is will be in both branches, right? So let's draw it like that. If I have my slider and it's fully out, So this is just now like a parallel circuit, right? Let's say our battery is 3 volts.
So the component is 3 volts?
That's right. Did everybody get why?
Yes.
Tamer, explain.
Oh shit.
Now you're on video.
I cannot do such a
It's the
thing.
same except
It's a parallel circuit, so
Faraz,
They
tell me.
both
Oh,
have to
sorry.
drop 3 volts.
Alex, tell me.
parallel circuit, so we know that when it goes through the resistor, it has to lose all 3 volts. So when it goes through our component, it also has to lose the same 3 volts.
Yeah, can anybody explain that conceptually?
both paths.
What's the- oh.
Zero.
But right now, isn't it zero resistance?
Component path, it will dump off all of this load there and then.
So if you're a truck, are you gonna go through both of these paths?
No, but regardless of the one you go, you're gonna drop.
So our Coulomb truck might choose to go through this one. It's only got one component in its loop, right? So it has to drop off everything at that resistor. If I decide to go this way, it also has to drop everything at that component. So this is gonna be 3 volts here. It'll be 3 volts here, and it'll also be 3 volts in the other
How would
resistor.
it lose 3 volts on the top if there's no resistance?
There is resistance.
But not when the slider's at the end.
All the way to the right, so there is no resistance.
There is no resistance.
What slider?
Wait, what?
Why would you say that?
Isn't there
It's
zero
the
resistance?
single
without-
slider. The
No, but
single
the
circuit
seed has
has zero
resistance.
on it.
This has some resistance,
Yeah,
right?
but if it only goes to the top, I mean.
Well, how many? Just assume that it only goes through that. How many volts would it drop? 3, and that's what it's doing.
No, current, not volts.
That's right. You would not have full current here, but you would drop all 3
You would have
volts.
more current on the bottom than at the top.
That's right. Yes. Okay, so let's draw it this way now. If I have this so that it doesn't go through anything here.
It would be 0 voltage on the resistor.
Almost all of my trucks are going where? Through the resistor. They're not going to bother going down through this. It has some resistance, right? So almost all my trucks are going to go this way. And so now it's kind of almost like a series thing, right? And so this is going to get all my 3 volts. So how many volts get dropped here? 0. It's going to have to do some, but it's going to be a really small amount. So this is effectively 0 volts. So this is a potential divider circuit. That's how you do
So
it.
if it was in the middle, would it be like 1.5 volts or something?
Yeah, that's right. If it's in the middle, you're going to have half your resistance out here. So you're going to have to drop half your voltage or so. So if this part has 1.5, then the other has 1.5, and you also have the branch here, right? Now that's not going to be perfect because you have to calculate these resistances with the inverses and all that stuff. So it's not going to be exactly half because there's going to be a lower resistance in the first half because you got another branch, but it will be a portion of each. Yeah, Alec.
Is this internal resistance going to turn up all this?
Do you want it to be?
Terminals can't help this.
My intention was to give you all these details today and kind of tie up current electricity so we can start EM tomorrow with my other group and on Thursday with you guys. And then on Wednesday I was just gonna do like the basic, not basic, but like the circuit stuff we've done before this.
Let's do that.
These are kind of details that IBE wants you to know and they think they're special. And
Refer to the terminal.
It's supposed to be a quiz at least.
Yeah, this specific concept.
yeah, so that's fine. The one thing I am going to get you to do today is the internal resistance part. So this bit, you have a choice. We can do it, I can turn this video on. We can do it in real life, or we can do it with